Good morning, friends. Good morning, my dear students. So, today let's talk about the refrigeration systems in thermodynamics. So, before going to this refrigeration system, let's talk about the aim of the session. So, the main objective of this session is to understand the basic concept of refrigeration, and the most referred instructional objectives of this session is how to determine the coefficient of performance of these heat pumps and refrigeration systems, and what is the significance of this refrigeration system in bioprocessing, particularly in biotechnology. So the outcomes of this session is students can able to understand the mechanism of refrigeration in bioprocessing, and students also can solve the numericals related to the coefficient of performance of refrigeration systems. Okay. So what is the refrigeration system? It is a device which can be used to transfer the heat energy from cold environment to warm environment by providing mechanical work or electrical work. This device is called a refrigeration system. It is quietly opposite to the heat engine. In the case of heat engine, that is a device that converts the heat energy into mechanical work. Okay, but whereas refrigeration system, it is the device that transfer the heat energy from the cold reservoir to warm reservoir by providing electricity. Okay. So refrigeration system can be used to create the cooling effect of the indoors or domestic houses. So this efficiency of the refrigerator is measured in terms of coefficient of performance, particularly in engineering calculations. So let's talk about the how to determine the coefficient of performance of a refrigeration system. So there, if you look at this block diagram, there is a two reservoirs, hot reservoir and there is a hot reservoir and low temperature reservoir. Hot reservoir or high temperature reservoir. So if you want to transfer the heat energy from the low temperature reservoir towards the hot reservoir, requires the energy. Without work done, without mechanical work or electrical work, it cannot be possible to transfer the heat energy from the low temperature reservoir to high temperature reservoir. Okay. So this is the simple block diagram for the refrigeration system. If you provide the electricity or mechanical work, then it can able to transfer the heat energy from the low temperature reservoir to high temperature reservoirs. So right hand side we can see the formula of the coefficient of performance of the refrigeration. So how to define this one? Same, desired output by required input. What is the desired output? Q2. What is the required input here? W. Required input means electricity is required for operating this refrigeration system, and the desired output is the Q2, that is the cooling effect. How much cooling effect maintained? Cooling effect maintained for the domestic houses or in-home houses, that is called desired output here. So this can be written as Q2 in terms of Q2 by Q1 minus Q2. As for the energy balance equation, W plus Q2 is equal to Q1. So we can get the W in terms of Q1 minus Q2. Okay. So what do you mean by coefficient of performance of a refrigerator? It can be defined as amount of heat absorbed at low temperature for amount of heat work. So in mathematically it can be defined as desired output to the required input, right? So what is desired output here? Cooling effect. what is the required input here? Work that is produced by electricity or electricity. Amount of electricity is applied to the system. So, in terms of notations, QC by W. So, QC by W, W can be rewritten as in terms of QH minus QC as for the energy balance equation. So, if you rewrite this equation in terms of temperatures, cold reservoir temperature Tc divided by high temperature reservoir Th minus cold reservoir temperature. This ratio gives the coefficient of performance of the refrigerator. Okay. So, this Carnot cycle can be used as a model of the ideal refrigeration cycles, because all the refrigerators operate in between the same two thermal reservoirs. The maximum coefficient of performance is attained by one of the based the Carnot cycle. If you look at this diagram here, there is a two isothermal process and two adiabatic process are involved in this Carnot cycle. Theoretical refrigeration system in terms of Carnot cycle. So, this is what we discussed the formula, how to estimate the COP of the refrigeration system in terms of temperatures. So, T2 is the cold reservoir temperature, T1 is the high reservoir temperature. Okay. There is a limitation here in the refrigeration system. So, practically 100% efficiency or performance is not possible for the case of heat engines and refrigeration systems. Let's talk about some commercial examples of the refrigeration systems. So, many industrial processes requires large quantities of liquid air or liquid ammonia, liquid carbon dioxide or ice or cooling water or brine solution. So, these are used for the industrial process for cooling effect and heating effect. So, the production of all these liquid forms from the gases requires a large amount of cooling energy. So, if you want to produce a large amount of cooling energy or cold water, requires the refrigeration systems. First examples are freezer, air conditioners, minus 20 freezers, minus 80 freezers. These are the generally used in the bioprocess industries. Okay. So, let's talk about the